Irrational Numbers version 14 by Edward and John Slevin. Woodcock Hall. We are at a critical stage in the ascent of man. We are establishing with a very high degree of certainty that our reality is following the dictates of mathematics. This leaves us many questions, which we may never be able to answer. However, there is just one question that we might be able to answer with profound consequences. Is the existence that created us a great deal simpler than we are, or is it very complicated and may require a creator? If it was more complicated, then one has to speculate who made the more complicated universe. It would show with great insight if we could prove, beyond doubt, that in fact, our existence could exist in a universe that is a lot simpler than we are. By a lot simpler I mean on a par with something like the eye, for example. There was a time when it was acceptable to argue that the whole world was created by design, just on the basis of the complexity of the eye. It has now been established that this has happened at least 5 times on the Earth, and each example can be seen as a progression of attempts following the dictates of Darwinian evolution. It's no longer acceptable to argue for the existence of God via this route. There are few gaps left for God to be squeezed in, and one of them is the origins of the universe. It would therefore be critical if I could show that our existence was simpler than the eye, for example. I intend to show that our existence can be explained by a very large number of very simple items. If we could do this, then there is nothing to say that our existence is no more than a progression to simpler and simpler existence back until the ultimate simplicity of Krauss is nothing at all. This at least is plausible rather than the alternative view of a more complex creation than us, which was created from progressively more complex creatures or existences. So existence converging to progressively simpler existences is so much more elegant than existence diverging to higher and higher complexity. If you are already familiar with the concept that the quantized, or discrete, attribute of string theory may allow computer modeling, go to Chapter 2. Chapter 1. Requirement. In fact, we are quite happy that converging, for example, can lead to nothing more than one irrational number which, although we cannot visualize or even write down such a number, we understand its existence and can work with it in a practical way as if it was calculable. We do this all the time with pi, for example. It may surprise you that if we can show that all irrational numbers required for mathematics to model the universe can be calculated to sufficient accuracy for this purpose, then the universe which begat us is simpler than we are. Although pi is impossible to even write down, we understand and use convergence to work it out accurately enough, so the error we always have is not a problem. All we need from pi is to be able to calculate it accurately enough for our immediate purposes. If we can show there is an accurate enough figure which is adequate for modeling the universe, then this would make the existence that begat us simpler than if pi needed to be infinitely accurate. This may seem a brash simplification, but I intend to show that all irrational numbers which are needed to model the universe do not need to be infinitely accurate, and can all be calculated to sufficient accuracy, and once this is established, show that modeling is more than possible. It is quite likely. I appreciate, proof alone, that there is a limit to all calculations. Accuracy requirements is not sufficient and several additional steps are necessary. However, I can then postulate a way in which the limited accuracy mathematics is done, which follows on from this deduction, which completes the proof of a simpler existence. So, I would like to postulate a model of our existence which allows for a simpler starting point from us to create our existence. I would then like to show that this simpler existence actually has perfectly plausible answers to quantum mechanics and photon-wave particle duality. Even Einstein's dilemma of spooky action at a distance is explained. I would like to do this by considering what we are all by now used to, that of a computer and a program. This does not prove that we are a program in someone else's computer, but is merely a vehicle to help our understanding of reality. In fact, I would like to emphasize that using the computer model in no way demands that the computer was developed by a creator. So long as we can prove that our existence exists in a simpler environment than ours, call it a computer if we like, it is more likely than otherwise that existence exists in an even simpler existence, etc. I want to emphasize that in the end this computer will turn out itself to be very simple indeed and could be no more complicated than the eye, for example. So don't jump to the conclusion that if it's a computer it must have a creator. Although we are starting out by postulating a computer, This computer will turn out to be so simple that we could postulate that it is too simple for us to call it a computer by comparison with our computers today, in the same way Babbage's calculator was only a machine. Okay, you might say you can simulate anything with a computer that followed the dictates of mathematics, but I intend to show that this universe is particularly configured to make the computer easy to construct, and features such as black holes or even spaghettification in black holes is designed to deal with calculation limits of a digital computer. Even the speed of light is a construction to allow the wiring of the computer to be elegantly simple. It will be that if we can actually conceive of a computer which models entirely and completely our existence, it will be a useful tool in which to speculate more things about our existence, to take us to a new level of understanding, particularly if I can show that we can work out what the program in the computer is. I can hear some of you saying that this is impossible, because we cannot even model the motion of the planets to sufficient accuracy to predict their motion over long time spans. This is not a valid argument because we are not aware of the starting point to any accuracy, and for example you getting out of the wrong side of the bed, given sufficient time, would change the course of the planets. Please bear this analogy in mind because this analogy, rather than the more usual one of a butterfly wing, will help to explain later concepts. Just because, at the moment, we cannot measure the starting points of the planets, or even the number of planets, accurately enough to get the same answers as the celestial computer, does not form a valid argument against its existence. In fact, the celestial computer has limited accuracy itself, and not only would our model have to be accurate but it would also need to make the same rounding errors, a much more difficult task. I am postulating a computer which controls the whole universe, so if this gets it wrong it will affect future existence anyway, so it cannot be wrong. In fact, it does get things wrong with rounding errors at every stage, but I will show that these rounding errors manifest themselves as quantum mechanics. I would like to continue this concept as if our existence was a computer simply because we can understand this. Also, I propose to calculate its size. Once I have demonstrated the design of the computer I am going to ask some questions which have troubled us for over 200 years. For example, how can light be both a particle and a wave and follow the dictates of waves when measured as a wave, but suddenly become a particle if we are looking for it as a particle? This dilemma is elegantly answered if we consider the computer which defines us. This elegant answer even deals with the way small numbers of photons behave simultaneously as both a wave and a particle. This problem is not dealt with either as a wave theory or a particle theory at the moment. It is partly explained by quantum mechanics, but this is totally beyond human visualization. This solution provides an explanation which anyone can appreciate. For those of you who are reading this without having considered whether light is a particle or a wave, I would point out that it's generally considered that when light hits a green leaf a photon particle causes a chemical reaction with sufficient energy to provide the power for the tree to grow. When you tune your radio to a frequency you can find a single frequency which is carrying sound. So light must be a particle and radio is a wave. But if light is traveling away from you at sufficient speed it becomes a radio wave, so light is just a higher frequency radio signal. This is the unsolved dilemma of the wave-particle duality problem I am going to address. If you want to detect light as a particle you can do this, and if you want to build the equivalent of a radio receiver for light it will look like just a wave on a lake. So to use the computer analogy, the formulae we see in our universe such as E=mc² are software programs in this computer. These programs can easily be automated provided they do not require any irrational numbers in the model of the universe, that cannot be simulated by a limited accuracy calculated irrational number. The first essential in developing this theory is to remove the necessity for infinity and its reciprocal, the infinite number of divisions. We can have the value 0 but not infinitely small values. Once we do this and then show that combined with the other fact we know that information cannot travel faster than the speed of light, then an explanation of our existence follows on. Irrational numbers are unique in that they cannot be calculated to perfect accuracy. If they are required to be calculated to infinite accuracy or there is an infinite number of them, then our existence is dependent on an existence which is more complex than ours. So, we need to show that our universe can be modeled with a finite number of irrational numbers, all calculated to finite accuracy. If we can prove this, then one can say that the universe which caused us is simpler than our universe, and does not need to be more complicated with all the ramifications this creates. I propose explaining that our world is modeled with a finite number of irrational numbers which are all bounded. By bounded, I mean that there is an upper limit and a lower limit to each value, and the value cannot be infinity or infinitely small. This lower limit is also the smallest change in value in all cases to date. So, in other words, the irrational numbers can all be calculated to sufficient accuracy to model the universe, as we do with pi. In proposing this, I can show that the existence which brought about our existence is simpler than ours, and as a backup to this theory I am going to explain the problem in very simple terms that the photon is both a wave and a particle. This dichotomy has never had a simple explanation before, or even an explanation that can be understood and visualized. This explanation also provides an insight into quantum mechanics and provides an explanation for quantum mechanics that anyone can understand. Therefore it is apparent to me that if life on Earth could in fact be a computer in an alternate reality, then it must be capable of being modeled with a finite number of irrational numbers. If the number of irrational numbers is bounded and the numbers themselves are bounded, i.e. not infinite, and these numbers are all related by mathematics to create our universe, then only a finite size computer power is needed. In our four-dimensional existence, 3D plus time, there is a very limited way in which irrational numbers are needed for our existence, and we can establish that all but one of them, gravity, is already bound. Where another milestone in our understanding may be uncovered within months if not weeks. When the last way, gravity, that irrational numbers could be infinite is proved also to be bounded. In 2020 great minds are looking for the graviton, the smallest particle of gravity. If we can show that all the different ways in which the finite number of irrational numbers can be needed to model the universe, are in fact all bounded, and we have proved that the total number of irrational numbers is bounded, then the possibility that we are in fact just a more complex version of our parent universe is highly probable. For example, I am going to show that even the irrational number pi is only needed in a bounded form, which can be accurately enough calculated, so is subject to calculating by a finite size of computer. However, for all practical purposes, if we accept the premise that we are a simulation, then it will provide an improved understanding and explanation of all around us, just as other postulations have done in the past. Chapter 2. Prove. I will now list the ways in which irrational numbers are in fact needed in modeling our universe, which are all thought at this time to be bounded numbers, leaving gravity as the only item left which may or may not be bounded. In fact, the model of gravity presented here is so elegant that many people will be prepared to consider that gravity is bounded just to satisfy this model alone. 1. First, let's check if we have a limited number of irrational numbers required for the mathematics numbers such as pi and d, which we know definitely are irrational, are required by mathematics. For example, pi is needed to calculate the orbits of the planets, but it is quite likely that mathematics itself is bounded, so the number of constants required by mathematics is also bounded. By bounded mathematics I mean that there is a limited number of formulas to totally allow the calculation of the state of the universe from its present state to a new state later in time. By the time I could mean the next iteration of the computer program. By maths being bounded I mean there is an upper limit to the number of formulas needed to model the universe. We cannot at this stage predict how many formulas we are going to need to model the universe, but we can say that so far the formulas have been surprisingly simple, and have advanced our knowledge greatly each time another one is found. At the rate we are finding formulas and the improvement in our understanding which occurs each time a formula is found, we would accept there are likely to be less than 1,000 in total, and each one requires 0, 1 or 2 at most irrational numbers. So therefore, it is very likely that the number of irrational numbers such as pi and d is in itself bounded, and could be less than 1,000 say, and could well be as low as 42, fulfilling celestial prophecy. So it's quite reasonable to say that first off the total number of irrational numbers required for the formulas which control this universe is bounded. 2. Numbers such as c, the speed of light, which I have not yet shown at this stage, are rational, but since they are used only in mathematics which is bounded, it is only important to show c it's rational. We don't want any irrational numbers which are not bounded to exist for our simulation to be conceivable. C is units of meters per second, so if we can show meters and time are bounded, then obviously C cannot be either infinite or very small, making it bounded. Let's deal with length, i.e. meters first. Smallest length. 3. The 3 degrees of freedom in our three-dimensional universe are now considered bounded at the low end by the Planck distance 1.616 times 10 to the power of minus 35 meters. Also there is a Planck time, 5.39 times 10 to the power of minus 43 seconds, from quantum mechanics. This puts a limit on the smallest possible length. Now the largest length. The total number of separate instances of Planck's length can be considered as bounded by the present extent of the knowable universe. 14.26 gigaparsecs or 46.5 billion light-years or 4.40 times 10 to the power of 26 meters, in any direction. The observable universe is thus a sphere with a diameter of about 28.5 gigaparsecs or 93 billion light-years or 8.8 times 10 to the power of 26 meters. Please note that one could postulate that the behavior of the knowable universe, i.e. that which exists between us and the microwave background radiation, could be being influenced by the material in the unknowable universe, which could still be infinite. This is not the case apart from a limited extension I will come to, and we only need to concern ourselves for the model with that material which is contained within the known universe. The reason for this is since we only see the material as the extremes of our universe at the beginning time of the universe, any influence matter has which is beyond our knowable universe, is not needed to be modeled at time now in our computer because its effect on us would have had to be before the origins of the universe. But the house skeptics among you will say, supposing we got in a spaceship and traveled at near light speed to a point nearer the extent of our known universe, then we could see further than the known universe, and this new material would have to be taken into account, and our model would have no data on this new material, so it would prove that my model could not be correct. It is this answer which prompted me to develop this theory. The answer to this is quite simple. The universe is expanding at 72 kilometers per second per megaparsec, roughly 3.3 million light-years, meaning that for every 3.3 million light-years further away from the Earth you are, the matter where you are, is moving away from Earth 72 kilometers per second faster. Let's do some very simple primary school mathematics with these big numbers. First, how many parsecs would we need to travel to go from one end of the universe to the other? 46.5 billion divided by 3.3 million. So how many km per second is the universe is losing material? 72 times 46.5 billion divided by 3.3 million. This is 72 times 14,090 equals 1,028,636 kilometers per second. Let's compare this with the speed of light, 299,792 kilometers per second. So the universe is expanding at 3.43 times light speed. We only need to travel in one direction to head towards the end of the universe, so we need to travel at 3.43 divided by 2 to move closer to one end, i.e. 1.71 times the speed of light. This means that no matter how fast you travel, the limits of the known universes are moving away even faster. So the edge of the known universe is continuously receding at a faster rate. It's not actually a coincidence that the outer limits are traveling away from us at just out of reach speed, but it's very useful for my computer. So in fact no more data is required if you travel away from our solar system. And in fact data is being lost at an alarming rate, which one could argue is good for the model, as our existence may get more complicated over time. Data at the far reaches can be disbarred, allowing the computer to stay the same size. So this other material outside the known universe, there must be some, because it's continuously being lost from our universe, as head on our outer limits is of no further consequence on our simulated universe, although it would have had some influence in the past when it was within the known universe. But this would have been taken into consideration at the time. This fact is immaterial because the past is, most likely, thrown away as the computer model progresses. This leaves the question as to how it happens that we can see particles down to the frequency of the microwave background radiation, a particle which has long since fallen off the edge. This insight provides a good insight into the operation of the celestial computer. The particle's original location has fallen off the edge, but since the particle was coming our way, its information is preserved, or at least some of it, so that when billions of years later it arrives at Earth it can be brought into consideration again, even though it has lost its original home. So the computer treats all particles in a two-part process. By taken into consideration, I mean that the first part of a two-part process has completed the particle or whatever has been calculated to exist, and has certain properties. This is then remembered by the computer. This fact is retained until the particle interacts with something else. This can be any length of time. At this second part of the calculation, the result of the particle's existence is determined. Now I need to go into a little more detail here to be more rigorous. We must not make the mistake that all other philosophers in the past have made until conclusive proof has disproved it, and sometimes not even then, to say that we are at the center of the universe and the universe exists to support us only. So our model must work also for alien life in any place in our known universe. Even this may be a little presumptuous, as there may be more to this universe, and indeed many universes, but if this is the case I would be happy to abandon this approach and just call it a good try. However, if this approach predicts something which other models do not predict, then this model is likely to be correct. So to make the model work for us and also work for an alien life form many galaxies away, or even falling at this moment off the end of our known universe, requires the model to also cover the known universe, and requires us to have a model with more data in it. However, never in the past when we find another layer, such as when we found the Milky Way galaxy was one of many, has the word many turned out to be infinite, so it's a reasonable assumption that the number of universes which at one time were known to this one will also not be infinite, and is bounded. On this assumption that my model will not collapse because there are many possibly overlapping known universes, I will certainly continue with this model. So the dimension variables are limited at one end by the Planck distance and at the other end by the limits of the knowable universe, a maximum value of 10 to the power of 27 divided by 10 to the power of minus 35 meters, or 10 to the power of 62. So every position in space of any particle can only be an integer number less than +/10 to the power of 62 from each other. Note for those of you who dropped mathematics at age 8. Sorry to bring in some secondary school maths, but this is very simple. If you consider that 10 to the power of 62 just means 1 with 62 zeros after it. It's just a construction that allows me to save writing a line with 62 zeros. This means that at no time does the irrational number pi need to be calculated at a better resolution than this 10 to the power of 62. But what size computer is this? Every zero added to the left of a decimal number requires between 3 and 4 extra binary digits added to the word length. So to recall a location we require 3 numbers, one for each axis, to an accuracy defined by a binary number of less than 244 bits. If the celestial computer is a binary machine, then 256-bit word would be perfect. So we currently build computers with half this length, and the increase is always doubling in length, so we are not far away from 256 bits ourselves. This makes a main rational number that we are familiar with bounded and calculable for all cases in our simulated universe. This puts bounds on the accuracy required of pi. Now let's deal with electromagnetic radiation. The material universe and electromagnetic phenomena on the largest scale. This is bounded by the knowable universe as above, and at the small end, string theory is now providing a model as an extension of quantum mechanics which simplifies all matter to wave mechanics, and strings are all integer values only. I know there is conjecture as to the correctness of string theory, however it's the best predictor we have about particle behavior at the moment, and certainly its quantization of reality is proving to be a very robust theory, which is the only part of this theory which I need for my proof. String theory explains electromagnetic radiation, and although it is known at this time that all the particles involved in string theory can only take on integer values, the number of bits for each variable are not fully understood. I suspect that, although the location in time and space can be fully defined in a small number of 256-bit words, there is nothing to say that the process which calculates the next Planck time uses internal registers to higher accuracy than this. Then the answers are rounded down to store them away for the next Planck time calculation. Now let's deal with time. This is a very interesting one. 5. Time is bound at one end by the time of the Big Bang and at the other by now. Our simulation does not need to go back further than the Big Bang and does not have to predict the future, as it just creates the next moment of time from the data it has about the state of the universe now. So now plus 1 is as far as it needs to go. So the largest time can be as 13.8 billion years, 4.35 times 10 to the power of 17 seconds. Time does not have to be recorded as to what happened in the past, only the present state of the universe needs to be recorded to allow the calculation of the next Planck time interval, 10 to the power of minus 43 seconds, so you could say that time only has two values, the old value and the new value, calculated every 10 to the power of minus 43 seconds. It's not quite that simple because, for example, a photon which was emitted a long time ago can hit our eye, or instruments today, and must be dealt with, and its redshift will be a function of how old it is. This means that any particle being modeled must have recorded about it, the time of its creation or some equivalent data such as its redshift. We have already said that Planck time is the smallest unit of time, 10 to the power of minus 43 seconds. So time can be an integer of value 0 to approximately 10 to the power of 61 Planck time intervals. Previous time is not needed anyway from the computer if it remembers the creation time of each particle. All the computer needs to do is calculate the next Planck instance from the last one, so not only is time bound but it's not needed for the computer simulation, anyway, apart from the recording of the creation time of each particle. Interestingly, the computer word size required for time is almost the same as that for location. Some interesting facts can now be postulated about our simulated world. No number higher than that which can be stored in a 256-bit computer would be necessary for this simulation. This is little different from modern computers. Computer memory is being freed up all the time by matter falling off outside the knowable universe. This may be sufficient to ensure that the computer's size does not need to change over time. Little to zero information is required to exist before the Big Bang, so the program can start in a unified, easily configured way with low complexity. The simulation need not record previous data, as moving back in time will never be needed. I.e., it may be quite conceivable that it's impossible to calculate backwards from the state today of the universe, what it was like previously. The computer simulation needs to do nothing more than calculate the next time positions for all the matter in the universe to fully execute its task completely. The calculation of the position of the universe at the next Planck instant must be possible, i.e., the calculation must not be circular in the way which makes everything in the universe dependent on everything else to calculate the next step. What better way to solve this problem than have a limited speed to information, i.e., a maximum light speed? So thousands of computers can work in isolation to calculate the next Planck instance, without worrying about particles arriving in its sphere of influence during the calculation. The process works like this: any number of parallel processes look at a small area in 3D space and calculate the coordinates of, and particles in the next Planck time. After this process, all traveling items have their new location calculated but are ignored if they do not result in a particle interaction. If they do involve a particle interaction, some of the details of this particle are added to the process load which is dealing with that part of the universe in the next Planck time. Then the first process is repeated for the second Planck time, etc. This model allows for multitasking and makes the whole model work with a large number of simple processes. 6 results in the unusual property that only limited information is required about each particle. This is reasonable because you don't want to have to store massive amounts of information about each photon, for example, while it's traveling halfway across the known galaxy. You only calculate its spin and other properties when you decide to destroy it in a collision. After each Planck time calculation, each microprocessor needs to communicate its results to its neighbors, and exchange any particles which have passed out of one water into another. It only needs to communicate with its immediate neighbors. The above list I consider puts all aspects of our universe into the bounded reality except one item. This item is gravity. It is conceivable that gravity itself may be proved to be quantized within my lifetime, and I am already well beyond retiring age. If this happens, do we then postulate that we are in a simulation, or do some of us start writing now on the assumption that gravity is bounded? This whole discussion is based on the assumption that it will be proven that gravity is bounded. Chapter 3: The Computer Design. So let's postulate the simpler machine which can model our universe. To start with, it only needs a small number of memory cells to fully represent each one of a limited number of subparticles that represent, say, each elemental particle. It will need to know, for example, its coordinates in 3D space, including its spin and velocity. None of these variables can be shorter than the Planck's length or bigger than the size the universe has expanded to at the time in question. We then run the program on these positions and other variables to get the answer for the next moment in time and add more memory to allow the progress in time by 1 Planck's time if necessary. After this, results are posted to adjacent microprocessors, followed by a check to see if adjacent microprocessors have anything to post to you. This is very elegant. Now let's investigate the consequences of this arrangement. Now let's deal with the note of velocity. Velocity is all things to all men. There is velocity as defined by the distance traveled and the elapsed time as seen by the particle itself, and there is a different distance and time as seen by everything else in the universe of the particle's motion. This is easily explained if you consider that the simulation does not bother with the calculation of the new position of a particle if it is not likely to be involved in a collision. At one extreme, a photon traveling at light speed will not be involved in a next time calculation unless it may result in its interaction with the rest of the world. At the other end of the scale, an aircraft traveling around the Earth will occasionally skip its inclusion in a Planck time calculation, as its velocity will occasionally, due to rounding errors, not require any changes at all, so the whole plane will be missed out of the calculation for 1 Planck time. A GSM satellite is a better example of this because we know we have to jump time forward for it occasionally against our earthbound clock. This will explain completely the relativistic nature of time, as the photon will see no time elapse between its creation and hitting something, and the Earth will see the plane has not aged quite so much as it has during the flight, but the Earth and the plane will all insist that the photon was traveling at light speed. Although the plane will have seen less Planck time intervals than the Earth for the same journey of the photon, the plane measurement of distance will be shorter as well by exactly the same amount, so the calculation of the speed of the photon will be the same on both time frames. This would happen, for example, if distance in any time frame was measured by counting Planck times and multiplying by the Planck distance. This would mean that light would always travel at the same speed in all time frames. This raises the interesting point about what speed the photon thought it was traveling at. Time for it was 1 Planck time, but the distance traveled as seen by the Earth and plane was enormous. So this explains when traveling at light speed you consider that to you the world is only two-dimensional, and in the direction of travel you cannot measure any distance. This is within 1 rounding error as predicted by length dilation in Einstein's theory, which produces zero distance. Your speed is completely indeterminate as you are at the limits of the rounding error in the calculation. You have stepped 1 Planck time because time is no more than the passage of Planck instances for each particle, so as you travel you see no change in the speed of a clock traveling with you, which will count Planck times exactly in time with you. For the slower object will use more Planck time pulses to time your journey, which will look longer in time. This allows all time frames to exist with their own interpretation of elapsed time, and all to have a different view of time and distance for something traveling at a different speed, and also allow a massless particle to travel at light speed and not require any unbounded calculation. Facts about our existence which are explained by this simple model of the universe. Why time only goes forwards as there is no record of previous time. Why the speed of light cannot be exceeded because time is only the number of counts of Planck's time as seen by that particle. The photon is already traveling from its source to destination in 1 Planck time. Times shorter than this are not possible, so speed is at its highest. Please also bear in mind that if we are in fact just a simulation, then the answer to the question which has troubled man from the later days of the Enlightenment, that of light's duality as a particle or a wave, is simply and elegantly explained as a rounding error in the mathematics involved in calculating its collision. The single-slit refraction experiment with an individual photon results in a Gaussian distribution of probability path of the photon is easily explained as the result of the rounding error distribution in the modeling of the position of the photon when its final position is calculated in our experiment. The reason we are of the opinion that particles are waves is that they diffuse and refract just like waves. However, there is another branch of mathematics which exhibits exactly these attributes, when considered on a large scale, that of error accumulation. We have only discussed so far one rounding error related to the speed of an object. What happens if the calculation is more complicated and requires a number of calculations, all only accurate to one rounding error? In mathematics this is called a random walk, or in the case of multidimensional string theory, quantum walkers, but I will refer to all walks as just random, in which you can add a rounding error in one calculation and subtract one in the next. If you do two calculations you can be out by 2 units or 0 units, and there is a 50% probability of either of these outcomes. As you increase the number of calculations, the most likely outcome is always 0 error, but there is a lesser and lesser probability of you getting all errors to cancel out, and a bigger probability of an increasingly large error. This curve of probabilities is called a binomial distribution. In its environment for large numbers of calculations, this gets closer and closer to a Gaussian distribution. And guess what? Diffusion results are also on a Gaussian distribution. So when we do light experiments which try to show the diffraction of light through one small slit, for example, the results we get from thousands of rounding errors, binomial distribution, as the particle bounces around trying to get through the slot in one piece, are indistinguishable from the Gaussian diffraction of waves. In the extreme case where the slit is less than one wavelength, and the interference pattern occurs, this could be caused by a resonance of the sphere of influence, which could be many Planck lengths, with the width of the slit. The same applies to the more complex example of several slits producing an interference pattern which looks like a wave. This phenomena is more complex to explain, and I have not thought of an easy way to do this and will almost certainly result in another paper. I will come back to this later with some general observations, but I hope this does not turn out to be like Fermat's last theorem. We postulate that light is a wave because it reflects and refracts like a wave and produces interference patterns and dispersions, as if it was a wave. Dispersion is the effect when you force a photon through a small gap. But the mathematics of rounding error accumulation giving a binomial distribution is not distinguishable when large numbers are involved, with the Gaussian distribution of diffraction. In fact, the two branches of mathematics are so identical that we can use either branch of mathematics to predict the behavior of large numbers of photons. This fact lets us conclude we are dealing with waves when in fact we are dealing with multiple rounding errors of each photon. However, the binomial error distribution will also model small numbers of photons as well as large numbers, so it does not require the duality of individual particles and large numbers of particles. So at the state of the art we learn at college in 2020 that we can consider large numbers of particles are waves and small numbers are individuals. This is wrong. The interpretation proposed here is that the particles are the result of mathematics with rounding errors. This view accurately deals with individual, the small number, and the large and very large number in one equation. How to model particles. Particles which travel at light speed or close to it. From our simulated computer point of view, a particle at light speed is fully defined by its starting state and its end state, which are only finally calculated when the particle has both been produced and collided or changed form or been absorbed. I will refer to all these forms as collided to make my description easier. For this description, particles start in existence when they need to be considered by the microprocessor and end life when this is no longer necessary because they are bound up or their individual string particles are bound up in something bigger. Or alternatively have been broken down into more basic particles. Each particle or group of particles such as a proton or an atom has a starting point and an end, and only trajectory matters between these two points. There is no need to calculate all the details about the particle until it or its entangled partner is annihilated. When the particle is created, this fact can be recorded, but many factors such as spin and other attributes do not need calculating until it is annihilated. Annihilated is not the correct term as its parts are never annihilated, but it's useful to think of the end of life as annihilation. One must remember here that the particle may be a light-speed device and sees no length measurement at all. Its point of creation and point of annihilation from its point of view are concurrent. The distance it travels is only calculated when it is annihilated, and only by ourselves. Distance itself may be a non-existent virtual variable in the celestial computer. This approach means that variables such as spin, for example, have no value or meaning until the particle is annihilated. This means that when one of two or more entangled particles encounters the end of its journey, then and only then attributes such as spin are chosen for one particle and imposed on the others at this time. The entangled particles may have been generated from some previous energy and particles with spin, angular momentum, etc., but the bookkeeping does not record anything it does not need, and these features are not needed again until annihilation. All particles and groups of particles have minimum information recorded for them, and there is no need to process this information unless a particle is about to be changed with another interaction. I call these events annihilations because the particle which was produced has a start moment and end moment and nothing else matters. Quite often a calculation will be undertaken on a particle only to find nothing happened. This must happen a great deal when a particle is passing through a transparent object. There is no effect on the particle apart from a very small percentage which do interact with the medium they are passing through, which is the reason the calculation was done in the first place. The vast majority just sail on through the material, but there are a statistical number of Planck instances where the particle calculation was done, so the particle slows down when passing through transparent material. This statistical number is called the refractive index. We do have the concept of entanglement to deal with. This can easily be explained as the fact that when two entangled particles are created, they do not exist as particles until one of them is annihilated. Once one is annihilated and it turns out to have a spin, for example, the complementary value must also apply to the entangled particle, which is updated with the information from the first annihilated particle. This new calculated data for the particle replaces the old insufficient data about the particles, so that the fact that it has downspin is decided for use when its annihilation occurs. In other words, the entangled particles exist in the same memory space as each other, and when any one of them has new data inserted, the other also gets the complement data. Don't forget this phenomenon only applies to particles at light speed which see no distance information, so they may look to us as if they flew off in opposite directions, but at the time of the calculation they are still next to each other. They do not part company and exist in vastly separated locations until one is annihilated. Now let's postulate the computing rules. Only integer maths is allowed, however it can have a resolution larger than 10 to the power of 62, but all interim or saved calculations must be rounded to Planck integers. There is some understanding at present that the Planck integers for some aspects of particles has a finer resolution than this. It's quite possible that, for example, calculations are in fact done to a higher accuracy than 10 to the power of 62, and when the final position is recorded it is rounded by some process to a 10 to the power of 62 integer. The whole of string theory could be purely the existence of an interim calculation to higher accuracy than 10 to the power of 62 for many variables. No information is retained about previous states of existence, a bit like an early text editor. There is no capability to back-calculate any previous state from the present state. This means the computer doesn't have to become exponentially larger each time a moment of Planck time passes. No calculations are made which may become redundant or unnecessary later. All calculations are completed at the last possible minute, and in addition to this all calculations are put on hold and the data for the rest of the calculation retained as soon as we are at a point where these calculations can be delayed. The computer executes the algorithm once for every Planck time. It can take as long as it likes doing the calculation because our only reality is Planck time. For particles traveling at light speed, no calculation is done until the possibility arises that the particle might be annihilated, so from the particle's point of view only one Planck time has passed between creation and annihilation, which is exactly what happens when traveling at light speed. Recursive calculations are possible until the error is less than 1 bit, in which case they can be closed. This happens with a twin slit experiment. There is no physical limit to the degree of multiprocessing. No information can continue indefinitely and be forgotten unless the information relates to matter falling off the known universe. The computer must ensure that at all times the sum total of all energy and its equivalent material and all spin are maintained. According to some cosmic bank accounts, this may mean that energy is conserved, or possibly that additional energy is being added all the time at some finite rate. The computer calculates the state of the complete universe every Planck time, but we only see when a particle arrives in our perception. Every Planck time the splitting of particles and other activities are calculated, but many particles are just traveling and no action is needed. These particles are missed out of the calculation and do not experience elapsed time. They are not even fully recorded, as some features such as spin etc. are not calculated until the particle's next interaction with the environment. Let's take an example of a photon which leaves the sun. At light speed, this is not involved in any calculations until it gets so close to another particle for the possibility of it to interact is likely, i.e. it's so close that it's likely to change the outcome by more than one Planck measurement. Say the photon hits a plant on the Earth. When and only when this happens, the photon is again included in the Planck time calculation. Now here is the interesting part. The photon has only experienced one Planck time in the 8 minutes it took the rest of matter to wait for it to arrive. This is even more interesting when the photon is slowed down by passing through the air. Now what happens is that the photon passes close enough to other particles for there to be a possible interaction. With it, the probability is that the photon will be undisturbed, but each time this is checked, one Planck time passes. This means the photon sees a speed reduction. We see this as the particle slowing down when passing through it. This process continues down to non-relativistic speeds, and so for example when a plane accelerates in our atmosphere and travels at 600 miles per hour, occasionally the whole plane skips a Planck time, so when it lands it has seen very slightly less elapsed time. This definition of the computer is not unreasonable, as it has been optimized for minimum data holding and efficiency, but interestingly this definition provides elegant answers to a number of questions. Schrödinger's cat. Schrödinger's thought experiment. Let's not use the dead-alive duality, as this is cruel and no one is postulating that a cat could. When the cat is first subjected to this experiment, we put the cat in the box. But when we put the cat in the box, no one remembered to write down whether it was black or white. In fact, more important than this, only the parts to make any type of cat were put in the box in the first place. This is a crucial difference to Schrödinger's postulation that the cat was alive when it was put in the box. However, irrespective of whether we knew, no one remembered to write it down. Just because you took note of the color of the cat when it was put in the box is irrelevant. The computer never wrote it down, and has no idea. It could ask you what color it was, so it could make it the same. There is absolutely no reason why the calculated universe needs to conserve the direction of spin between the production and annihilation of the particle, only that spin of the total universe should be conserved, not the individual values. If we say there should be 50% black and 50% white as for spin, then the microprocessor only has to define each new cat with an alternate color for the balance of the whole universe to be preserved. The box was locked from the time the cat was created until its requirement to fulfill its destiny, and the box was opened. As the box lid was opened, the parts were hurriedly assembled into a cat. Its final color is a matter of chance to balance each variable such as spin for the whole universe, just as the experimental results gave. We can no longer prove this is a dichotomy because we cannot remember if we even ever knew whether the cat was black or white on entry. In the case of entangled cats, one black one and one white one were put in the box, but only when the box was opened and a cat removed did the second cat know its own color. Sometimes rebuilding the cat is easier as the box is still intact and shut. Single slit light behavior. What happens when the box is damaged in transit? For example, if it is posted through a slit that's too small for it. This is a more complex problem requiring more calculations. More calculations means more errors, as all maths, as we have said earlier, are bounded, even interim calculations. Each time a calculation is done, an integer rounding error results. This can only affect the cat color in binary ways such as whether it's black or white, but each error affects non-binary variables such as position in what is referred to as a random walk. The way a random walk works is that each calculation results in an error which can be in any direction. If it's a vertical slit, we should be only interested in horizontal errors. As each error occurred, we move closer to the center of the direction or further away, say at random. But we can also go back or up and down as we pass through an undersized slit. This is classified as a quantum walker, as it's more complicated than a simple one-dimensional random walk. If we do enough mathematics and accumulate many errors, we get what is known as a binomial distribution of error probabilities. The most likely outcome is the straight line answer, but the probability of slight errors is great and the probability of large errors is small. The envelope of probabilities from a simple random walk is a binomial distribution. When there are many rounding errors in the calculation, such as a slit narrower than the wavelength of the particle, then the binomial distribution is indistinguishable from the Gaussian distribution we observe in diffusion through a slit. Also, as the slit is diminished in width, the probability of the particle reflecting from the slot instead of going through increases, and this is exactly as experimental results show, with the reflected angle also forming its own binomial or Gaussian distribution. Now let's postulate what happens when two slits are present. I said earlier on that I could not think of an easy way to explain this, but let's have a go. I am not saying that this is a postulation in the same way as previous ones. This is more of a surmise. As I said previously, the slit experiments need another paper. In fact, they also need some more experiments to find if the sphere of influence of a particle is limited. However, I would like you to consider which is more likely, that I am right, and the particle is sent on with minimum baggage, which is reconstructed when needed, so that the memory requirements for each particle is minimized. Or that 25% of theoretical physicists are right and believe that there are an infinite number of parallel universes, and we choose to join the one that follows our reality, or another 25% who believe this is ridiculous. They believe that the multiverse only produces an additional universe when we make an experiment, or one of the remaining physicists who is his personal speculation only, with less likelihood than this one. At the present time, no theory explains the twin slit experiment. Even quantum mechanics has not been able to explain the concept of checking which slit the photon went through, destroying the fringe and extra dispersion characteristics. I think we can safely say that the phenomena is created in the slits themselves, not when the particle hits the screen. The screen can take one of many forms. Let's say it's a large CCD array which sees greater dispersion and a fringe pattern which you would not expect unless the photon was a wave. I think we can safely say that we have two things to explain. One is the multiple fringe pattern, and the other is the wider dispersion than you would get from one slit. I would speculate that the problem occurs at the moment the particle leaves or enters either of the two slits. When actually passing into and through the slit, it is included in a Planck time calculator each time it could hit a side, for example. This causes ordinary dispersion on the angle of emergence from the split. However, the first calculation after it emerges from the undersized slit is that it finds the sphere of influence of the particle overlaps two slits. This would not be a problem if the slits were wider than the wavelength, as all particles could travel through individual slits. But if there are two small slits, it's impossible to be sure how the particle got through the grating. Obviously, the whole particle got through the grating because you cannot end up with half a particle. So half did not go through and half bounce back. There is only one Schrödinger cat. However, with two slits it is quite possible and even likely that the particle got through the undersized ones using both holes. This makes the calculation of the mathematics even more complicated, and as said previously, each calculation introduces the inevitability of a rounding error to the nearest integer. This results in an error probability, but we also know that when the particle was constructed it cannot annihilate itself. It has to appear somewhere or it would violate Rule 7. So the particle cannot land in a place which would require it to travel through the grating and annihilate itself. This eliminates a set of stripes where the particle would diminish rather than go back to its original state. Otherwise, from this, the error distribution is now more dispersed because of the number of rounding errors, so we get what looks like an interference pattern. This interference pattern is not caused by the particle being a wave, this is caused by the error distribution of many rounding events. So the whole idea of particles being waves is a misnomer. It's just that the mathematics of binomial random walk error distribution on a macro scale is exactly the same as wave mathematics. So for 200 years we have used the mathematical tools of wave theory to describe electromagnetism and now string theory with very accurate results, which we have mistakenly considered must be correct because its predictions are so accurate on a macro scale. The binomial error distribution works on the single particle and the very large number of particles. It also works on the middle ground of say 1000 particles. This, however, is only one of several postulations. An interesting experiment could be done in measuring the transit time of the photon. It's possible that the addition of the extra slot could increase the transit time of the photon, meaning that it has endured more Planck time calculations, each with a rounding error. This experiment might shed light on the process and show that it could have suffered many more rounding errors with a second slit. From our point of view, we can see only the particle behaving as a wave when there are many of them, but in fact the thing which is happening is that the individual randomness of many thousands of results is producing an error probability distribution which we think are waves. This is because errors produce binomial distribution that we cannot distinguish from a Gaussian distribution, and there is a pattern of stripes where no errors have ended up because this would violate law 7. So to us it's an interference pattern caused by wave interference as we know it from sound or even stone on water. There are not necessarily any waves at all with particles just obeying probabilities building up over thousands of examples. So to make it quite clear, a particle is a particle and not a wave. It's just that it can only occupy integer mathematical positions, so the error in position only makes the particle look like a wave when there are many of them. Let's drop the idea altogether that the particle is a wave. It's only its position which follows a wave probability distribution. Now we got that sorted out, let's deal with spooky action at a distance. This phenomenon is explained at the moment by postulating an information channel over long distances at infinite speed. This phenomenon is only applicable to particles at or near the speed of light. Even when a quark is trapped with its friends making up a neutron or a proton, they are still traveling at the speed of light. How this happens at the moment is unclear from string theory. Whether they are bouncing around at the speed of light or just spinning at this speed is unclear, but nonetheless, they are all traveling at the speed of light. If, however, the computer program treated the photon as a separate entity to its constituent string quarks, there is nothing to say that it leaves the string parts out of the calculation, because they can have no influence on the behavior of the proton, so they are effectively experiencing the same passage of time as a particle at light speed, so we consider that they are traveling at light speed, simply because they are being left out of Planck time calculations. In other words, the computer treats, say, a proton as an entity in its own right and emits the string particles the proton consists of, from Planck time calculation. This act alone would be sufficient for the string particles to all consider they have been traveling at light speed all the time they have just been trapped in a proton. This fact also gives a lower bound to the action of the single multiprocessor which models the universe. Once a string particle is locked up in a proton, for example, it is possible that it no longer needs to be considered in its individuality but is processed as a proton with its other string particles. This way, if the proton is ever broken up again, the string particle will again be considered in the next Planck time calculation. Meaning that only one Planck time interval passed between its appearing and disappearing, making it a light-speed traveler. This being said, then our three-dimensional universe loses at least one dimension, as light-speed particles consider they can travel the whole length of the universe in zero time. Therefore, light-speed particles are not separated in space at all, and I would conjecture that they are part of a matched pair existing usually as complementary with upspin and downspin and zero total momentum. At all times the balance of angular momentum etc. is conserved. One could argue that since history is not recorded, time is a binary digital function only now and plus one Planck time, and even these do not exist concurrently, so it's not a dimension like the three dimensions. And therefore our existence could exist in a four-dimensional universe, like ours, and still have a dimension available to deal with entanglement. The only reason we can see time history is because we reconstituted from the particles which are still in our existence now, and the date that they came into existence is recorded with each particle as its redshift. We then record history in our brains or by arranging particles in a book in a way which we can decode. Chapter 4: Time Travel. We cannot travel back in time because the computer does not remember past events. The computer only stores the latest copy of existence and neither has a copy saved away from previous time or is able to back-calculate how the present state arose. For example, for any particle only its present state is recorded. There is no data on how the quarks came together to create it, etc. We cannot go forward in time because the model of the universe program has to run for each Planck time, and it's not possible to predict the state of any particle more than one Planck time. To predict the future would require the building of a computer with exactly the same complexity as the one proposed here, including exactly the same rounding errors. No scale model is acceptable. This is obviously not possible, as it would result in a computer which contains a computer as big as itself, which leaves no capability for it to do anything. Time dilation. This leaves only the phenomena of time dilation. This is not traveling forward in time or backward in time. It's purely that a body in motion experiences the passage of time to be slower than a body at rest. By rest I mean that the body in motion is the one that has experienced some extra acceleration over the body at rest to increase its speed relative to the body at rest. This is a very interesting phenomenon and occurs as a result of the necessary sequence of events that must take place for time to move on one Planck time. Our celestial computer has to move on to the next Planck time in an orderly manner, which is part of how the computer works. To move on one Planck time is difficult to deal with, because where do you start? Because as you move to the next Planck time you have to stop time and recalculate a new Planck step. How much this Planck step equals the passage of time on any object can be set by the program, but it must be an integer or variables become irrational. So the program has an option to drop one or more Planck time from the measurement of time for any item. It does this by dropping the number of calculations it does for traveling items so that the program can cope with positions changing during the calculation of the next Planck step. The best way you describe this is to say what happens when the particle reaches light speed. At light speed, there are no Planck times between the origin of the particle and its eventual annihilation. This is because the distance dimension is 0 for light speed objects, so the light speed object understands that for it, only one Planck time has passed from its creation to its annihilation, but in fact, years of time could have been experienced by the item it reacts with. The computer uses this fact to deal with the dichotomy it is, because it cannot work out the next state of the universe from the last otherwise. Travel close to the speed of light. Say a photon is passing through a translucent object. Normally a photon traveling through clear space is not progressing in time from its perspective. This is because the celestial computer has no interest in the photon, as it has no effect on its surroundings, so it does nothing by way of calculating its new position as it just passes the photon on to the next microprocessor. It calculates the current position of the photon only when it is about to influence into something, but this is exactly what happens when it passes through glass, so the celestial computer needs to calculate this photon into the next Planck time. If the material has a low refractive index, then the probability of it interacting is small, and a high refractive index the probability is higher. Chapter 5: The wiring. Because light speed dictates the maximum speed that information can travel through the universe, it is possible to construct the computer which controls us as a very large number of simpler computers. This is a very important consideration. If the speed of information flow had been instantaneous, then every part of the universe could be influenced by any or even every other part of the universe, making the calculation of the next Planck time very complicated. However, because information speed is limited, each very small area can be calculated in isolation without considering the wider surroundings. For example, at the start of the Planck instance, every, let's say, molecule is surrounded by a number of influences such as very local chemical activity, a number of photons of the complete spectrum of electromagnetic radiation, and gravity, of which we do not know how this manifests itself at this time, 2020, and that's it. There are no other influences of the outside world to be considered. This means the computer can be a very large number of very simple computers. In fact, each calculation cell, or say microcomputer, could be so simple that we might be able to figure out exactly how it works or its program. The computer has two calculation phases which alternate. One phase deals with any particle which has to move out of its present microcomputer into the sphere of another microcomputer, or into or from a no man's land where it's so far from proximity with other particles that it's not required to be included in the next Planck time calculation. The second part is for the individual microcomputers to calculate what happens in their influence area. When these two activities are complete, then one Planck time has passed and the process is repeated. The no man's land calculation above may be an identical microprocessor with the same program in it but no molecule in it, which simply received the photons and gravity into itself and just decided where to pass all the photons and other particles to. The physical shape seen by ourselves of the area of influence of a single microprocessor could be any shape from tetrahedral to approaching amorphous. However, it's also possible that the boundary between adjacent microprocessors is a bit like the Americans, Chinese, and others, in the South China Sea and is not accurately defined. The only essential is that all particles are in one microprocessor at one time. A boundary is only needed to decide which of the adjacent microprocessors take on a traveling particle. I think the best way this would work is that at the end of the Planck calculation phase all the separate particles being handled by one microprocessor would be checked to see if they are departing this microprocessor because they are closer to the center of an adjacent microprocessor, or at least they were when the previous Planck time started, and this particle would be posted to the next microprocessor which would not have a veto on whether to accept it. This would mean that the sphere of influence of each microprocessor is calculated at the end of each Planck time only on the particles which may be emigrating to an adjacent microprocessor. Size of each microcomputer. As stated previously, each microprocessor cannot be smaller than a proton. It is also unlikely that a microprocessor could handle a complete molecule because molecules can be of virtually any length, can interact with other molecules in extremely complex ways. So I would postulate that each microprocessor models one atom and any fundamental particle in its territorial waters, for want of a better description. There are only about 120 different elements which are stable more than one Planck time, which could be covered by a separate program for each element, but it is unlikely to be even that many as there is significant duplication of behavior. The way it would work is by calculating what would happen in its own waters during the next Planck time. This could result in all manner of reactions including splitting of an atom and if an adjacent atom is pushing with sufficient force fusion. There is one more concept may help those who are still skeptical out there to be convinced and more than happy to appreciate I might have something here. The problem of each microcomputer having to be able to interact with every other microprocessor in the known universe to collect information before the start of each Planck time calculation and send its results to all other microprocessors that require it at the end of the calculation. This problem is solvable only because of the limited speed of light and information generally. The microprocessors handle a specific amount of the three-dimensional world. The average density of atoms in the known universe is 3 per cubic meter. So there are 3 microprocessors for every cubic meter in the universe on average. Most space is empty, so there can be many cubic meters with no particle, with only one microprocessor dealing with it. At other places, say in the center of the Sun, they are so closely packed that enough energy or pressure can arrive inside each one from its neighbors that it can fuse or split an atom. If this happens, a neighboring microprocessor can take a split and pass its atom to the next microprocessor and so on, or one microprocessor of a fusion would become redundant and take over the work of an immediate neighbor. But at no time does any microprocessor have to know any more than its immediate surroundings. This is because no information can travel more than one atom distance in one Planck time, so a microprocessor can be sure that it can rely on the fact that so long as it gets itself and its immediate neighbors correct, everything else will sort itself out. It is of course quite possible that each atom can communicate by any means with its neighbors, but let's think of it in our reality terms. Each atom requires to know the gravity, spin and proximity to other atoms it may want to react with. But these are all scalar vector quantities. For example, the gravity an atom experiences is a single force measurement and its direction on 3 axes, i.e. 3 integer values. It calculates this from its immediate surroundings, and this is communicated around the known universe at the speed of light, as at each Planck time as each microprocessor communicates with its neighbors. This is why the computer I am postulating is so simple, because it only needs to talk to its immediate neighbors, and the rest of the universe is only to take into consideration the information which has already arrived at its neighbors. Each microprocessor only needs to use information it can get from its immediately surrounding microprocessors. But I hear you say that each atom must know the forces from every other atom in the universe to calculate its new position and other variables. This is not the case, and the best way I can describe this process is to compare the situation of each microprocessor with that of a jar of sweets. If you add or take away a sweet from the thinner neck at top of the jar, every sweet in the jar notices. The angle they measure and the force varies wildly. The ones at the bottom just accept more weight, but the ones at the top can actually be pushed up against the glass rim, increasing further the pressure at the bottom. Every single suite takes a force or push in one direction or another. They know of a vector with an angle and a scalar value, i.e. one force number. They do not need to know the force from individual items, they only need one force and one direction. Each suite is able to measure the total pressure being applied by all jar neck pushers by measuring the forces being applied by each neighbor. It's analogous to my computer model because if we add just one suite to the neck, the additional force of just a few ounces or grams is transmitted immediately to every suite in the jar. In our case it's at the speed of light, but its effect is everywhere. This is exactly how gravity is passed to all microprocessors, who can then all rely on the fact that nothing will change during their one Planck time calculation. So by measuring the forces being transferred from adjacent microprocessors, it is possible that the gravitational effect from everything else in the universe is interpreted correctly by each microprocessor. An interesting point emerges here, which is the reason the graviton is so elusive. Gravity follows the superposition theory. For those of you who have not studied resistor networks in A-level physics, this just means the total gravity force is the sum of all the individual gravity forces. This means that gravity calculation is quite simple, using the gravity vectors of the surrounding microprocessors and your own mass. I would postulate then that this is calculated and transmitted to double precision, i.e., it could have 512 bits of resolution. This allows us to feel the force of the gravity of our local group of galaxies whilst still being able to deal with local higher forces such as those in the Sun. The 512 bits requires virtually no mathematics apart from addition, which only goes up linearly with word length. I would postulate that it's certainly got to be more than 256 bits. The reason I say this is that gravity has to work over the same distance and resolution as time and distance, but unlike these other variables is a square law in that if you double the distance you divide the force by 4 from Newton's work. The normal way that you would deal with this in a computer is to do the calculation to double precision, which deals with a square law perfectly. It is interesting to note that space and time require bounded irrational numbers, but gravity formulas do not, requiring little more than addition and subtraction to calculate the total gravity on any given mass. These calculations only increase linearly with word length, so double precision would only be twice as difficult, so this variable could be communicated at double precision. This will mean the graviton is going to be very elusive indeed, because its size is so much smaller than the other elements of our world. This would mean a calculator of gravity which each microprocessor has to pass on to its neighbors at the end of one Planck time is very easy, so it can be done to higher precision. Double precision feels about right, but we will wait and see. For example, all the microprocessors representing a piece of glass may at any one time contain a number of photons. Each microprocessor plays snooker with all the elemental particles surrounding its atom, and in the case of a photon may decide that it's hit its atom or may decide that it's missed, in which case it would decide which of its neighbors, there must be one, which is in the flight path of the photon, and it passes this information, with the minimum amount of baggage, to the adjacent microprocessor. At this point this model deals with the rainbow, which is very poorly understood with other theories. The higher frequency photons have higher energy than the lower frequency red light. The higher the energy of the photon, the more likely it is to interact with an atom in one Planck time, so as the microprocessor decided whether to stop the photon because it's dangerously close to its atom is affected by the amount of energy in the photon, so the violet photons are tested more often. This manifests in our view as a speed reduction for the violet light. As I said previously, this is the refractive index. So the refractive index of blue light is higher than red light, hence the rainbow. This is why when the photon arrives at the microprocessor which allows it to hit its atom, it has to choose the information which does not need to be transferred, such as spin direction, in what seems an arbitrary manner. I must concede that at this point the universe this computer is in has more dimensions than ours, because there must be an additional dimension at least which allows two entangled particles to still be next to each other in a fourth dimension, so that they can be separated by very large distances in 3 dimensions, but still be next to each other in a fourth. However, the existence of extra dimensions does not necessarily add complexity. At least the existence of a fourth dimension rules out the possibility that the Church of Scientology is right and we are run by aliens in this universe. So each microprocessor is like a balloon in an environment of balloons. If atoms are far apart, the balloons expand to several cubic meters. The shape of each balloon will depend on the forces being applied by other adjacent balloons, and the shape of their atoms. There will be an upper limit of the number of balloons in contact with any one balloon and could also be 42. So there is a limit to the amount of calculation each microprocessor needs to be able to do. Also, there are only 120 or so differently reacting atoms, each with a few isotopes which modify their behavior slightly. But this would hardly need 120 separate programs, as there is much duplication in the behavior of each atom of the periodic table. Black holes. Black holes are a result of the 3D space being modeled by each microprocessor approaching or arriving at one Planck length in each direction. As stated previously, all irrational numbers must be bounded. But also there are limits on the values of all numbers. For example, if you pack the balloons together with sufficient force that the size of each atom approaches a Planck length, it is no longer possible for the microprocessor to make any meaningful calculations, as any movement of a particle results in a rounding error which leaves the microprocessor with the same result as the previous Planck time. The effect on our reality is that a large mass is compressed into a very small space, of which no particles can be emitted because there is insufficient wiggle room inside each modeled space for any movement. Black holes therefore are a necessary requirement of the inability for each microprocessor to continue calculating new values at the extreme. When this happens in one group of associated microprocessor, there can be no exchange of information and the whole mass binds up with zero progress, from one Planck time to the next. All that probably happens is that additional microprocessors join the group, as near the event horizon there is a spinning sphere, actually more like a donut shape. And as atoms are jostled towards the axis of spin, they lose centrifugal force, and fall towards the center. By the time they reach the center, they have lost all possibility of meaningful maths, and passed on all their information to atoms behind them in the queue to join the black hole. There is possibly no other particle in the black hole other than the mass-producing atom, as these were squeezed out to the microprocessor behind in the queue to join the black hole. This would be a particularly elegant way of dealing with Stephen Hawking's black hole calculations, as all information would have been left behind at the surface. The process is called spaghettification, as the atoms line up to follow each other down the spaghetti to enter the black hole. The mass-producing items such as protons and neutrons go down a conduit of spaghetti, while the photons and zero-mass particles which are not attracted to the black hole are squeezed back up out of the black hole as the microprocessor runs out of wiggle room. This is the perfect time for each atom to have all other associated particles and electrons fed back up the spaghetti to the atom behind, which is suffering less gravity because it's a further distance from the center of mass. All that's left is mass with virtually zero information. The only information left in each microprocessor is the type of atom, a single integer between 1 and 120, and it may be a very restricted list of survivable atom types. In fact, there is no saying that the microprocessor sphere of influence follows their atom into the black hole. As I said earlier, it is possible for a microprocessor to have no atoms in it, just weightless particles. It is therefore quite possible that there is so little information left in the center of the black hole that just one microprocessor can handle it. In which case, as the atom tries to join the black hole at the center, it is taken on board by the one microprocessor and added to the very large single atom at the center. This will mean that the microprocessors in the spaghetti don't move at all. They are just a conduit to let an atom in one end and out at the other to the single microprocessor at the other, and push and heat photons with no mass from the one microprocessor to send them back up the spaghetti. This would effectively be the Hawking radiation everyone is looking for. This would help with another problem as to where do the extra microprocessors required to handle the information arriving all the time at the black hole. If microprocessors are not lost to the black hole, every microprocessor arriving at the information boundary stays there looking after its charges. From an observer's point of view, there is a point in space with large mass-producing gravity but very low emissions because the processors have shut down because they have insufficient dynamic range or wiggle room to produce any change in answer from one Planck time to the next. This would also explain how a hydrogen star such as our Sun collapses into itself and re-emerges as heavier elements. Chapter 6. Conclusion. First of all, it's clear that our existence has been carefully configured to minimize the design of our existence in simplifying the wiring and minimizing the amount of memory required for each particle. It is inconceivable that all this simplicity is thrown away by requiring time history to be remembered. We therefore exist in an environment with no time dimension, so it's not only impossible to extrapolate forward in time, but it is also impossible to calculate backwards to establish what happened. History is only recorded by ourselves. The universe is unaware of history. The only time is now, which has two states only. Before a Planck time interval and after a Planck interval, and only one of these exists at any one instant. At first I was puzzled as to how the whole universe had an absolute time of a Planck instant and how it synchronized this throughout the universe. This is not necessary. Any microprocessor can take as long as it likes to undertake the calculations required for one Planck instant and then make its neighbors wait. This delay will propagate around the universe at the speed of light, like any communication. So parts of the universe could be, say, 100 Planck time units in advance of others and will be slowed down when the delay reaches them. This, coupled with the fact that all particles have moved at one time or another and dropped some Planck instances, so it's no longer possible to either work out exactly how old the universe is, and more importantly the original location of the start point of the Big Bang is also lost. This is why now we seem to be an inhomogeneous soup with no center. We appreciate that each microprocessor may be in a place for which three-dimensional space is meaningless, but let's just for a moment imagine that it is also limited to 4, say, dimensions. I said earlier that the density of atoms in our known universe is 3 per cubic meter. It would not be impossible with our existing technology to conceive of each of these microprocessors being significantly smaller than the pollen grain. No communication apart from that with its immediate neighbors is required, so if we put a pollen grain microprocessor in a box with the others required, the box would be smaller than the Milky Way to simulate our whole existence. Someone looking at the box would have no idea it was anything more than a box of pollen grain, but our complete reality could be within its simplicity. Our universe appeared when one pollen grain cooperated with a neighbor pollen grain and so on. This rippled through the pollen and may very well be still rippling through, and so the universe grew. This ripple was not in our universe, so is not constrained to the speed of light, which is a constraint applied to our universe only to simplify the wiring of the computer. There are still things to be explained by this model, but it does not require an infinite anything, particularly an infinite number of universes. As I said in the first place, anything can be simulated by a computer if it's big enough. But I only have a burden of proof that it's simpler than we are, which I think you must agree I have shown. If you can find a property of the universe which you feel I have not addressed, then I suspect you should drop your line of inquiry, and you are much more likely to succeed by addressing this problem yourself using this model. Questions I have been asked. Q. How is it possible for the universe to expand faster than the speed of light? A. The universe is our reality, and is not in our universe. So the constraint of the speed of light does not apply in our universe's reality. It is interesting to note that it's only a bit faster than the speed of our light, and our speed of light might be as fast as it could be in a simpler existence. Q. You started by saying our existence was simple, but I don't understand your description of the twin slit experiment. A. Neither do I. There is more work to be done on this feature. Even after the 100 years of experimenting with it, no one has investigated the delay in travel time which a photon experiences when an additional slit is added. Even if there is zero additional time delay, this provides additional insight which is required to fully bottom this problem. In this respect, my solution is no worse off than any other modern postulation. I am expecting that further experimentation on this matter will be a two-way process and add to our understanding of the microprocessor program and communication with its neighbors. This phenomena is like a crack in the lid of the Pandora box, which explains more fully our reality when we finally open it. Q. How can things be real to us and yet not exist in reality? A. 50 years ago, I would have expected this question. I would suggest you ask a 12-year-old what it's like to be immersed in a computer game, for a complete answer to this question.